Welcome. A quick recap of what was covered in the last introductory lecture. We defined a beam and saw some of its basic types. Then we learnt about the supports and loading types, followed by the resisting forces and moment developed at any cross-section along the beam's length, which are called the axial force, shear force, and bending moment respectively, together with their sign conventions. These shall further be useful to calculate the maximum induced bending and shear stresses at a later stage. In this lecture, we shall consider an example of a simply supported beam with central inclined point load and use a direct approach to find the axial force, shear force, and bending moment at any cross section along the beam's length and plot these suitably in the form of corresponding diagrams. These diagrams shall allow us to quickly glance through and allow us to find the maximum of these values at some specified location. Let's say we have a beam of length 2 meters. I am purposely drawing a beam with some depth here so that you can have an intuitive feel of a beam without resorting to the usual schematic, that is, a line representing the neutral axis or surface. Let us label the left end as A and right end as B and the point C marked at the center of the beam. As explained in the last lecture, a simply supported beam is in general shown to be supported by one hinge support and one roller support instead of both hinge supports or both roller supports. Let's show the hinge or pin support to our left and the roller support to our right. Let's now show an inclined load of 5 kN acting at the center of the beam with the gradient of 4 units in y direction over 3 units in x direction, pointing in the southwest direction. We are now ready with the given data. We will first find the unknown reaction set up at the support points due to the inclined load, considering the entire beam in static equilibrium. The inclined load can be conveniently broken into two components, one vertical and the other horizontal. The gradient angle can be found by taking tangent inverse or arctan of 4 over 3, giving a value 53.13 degrees. Hence, the horizontal load acting towards left can be taken as 5 kilonewtons times the cosine of this angle to get 3 kilonewtons, and the vertical load acting downwards can be taken as 5 kilonewtons times the sine of this angle to get 4 kilonewtons. We shall now disregard the inclined load for our calculations and focus only on the component loads. The vertical load acts symmetrically over the beam, hence the vertical support reactions should be each half of this value acting upwards, that is of 2 kilonewtons. The horizontal load is balanced by a reaction force of the same value acting towards the right, developed at the hinge or pin support. The roller support does not offer any resistance to the horizontal load, hence no reaction is developed over here. At this stage, the entire beam is shown to be in complete static equilibrium with the unknown reactions found. We now shall proceed with the method of sections so that we could consider the static equilibrium of one of the parts created by virtue of an imaginary section, thus allowing us to show the resisting forces and moment developed within the beam's cross-section on the part under study and disregarding the other part created. The imaginary section shall be allowed to move from the reference end to the other end step by step, and we continue to find the now unknowns, that is axial force, shear force and bending moment for each part created and developed at the cross sections. Let's now assume some reference, say the left end, that is point A. An arrow is shown pointing towards the right from the end A, and a small letter X is marked indicating the distance of the imaginary cutting plane or section from the reference end along the direction of the arrow. This section or cutting plane divides the beam into two parts. We shall retain the left part for our calculations and disregard or virtually throw away the right part. Let us first take the imaginary section just to the right of end A, then halfway between points A and C, then just to the left of point C, followed by just to the right of C, then halfway between points C and B, and lastly just to the left of end B. Let's draw the left part under consideration for each of these sections created below the beam separately and consider each of these in static equilibrium. For this, we consider each of the parts drawn as a free body diagram, that is FBD in short. Free body diagram allows us to consider an entire body or a part of it in static equilibrium lying freely in space and isolated from the adjacent connected parts, and draw the resistive forces and moments instead. We shall virtually throw away the right part created in each case by virtue of the section. We show the axial force, shear force and bending moment in the part created by the first section and plot the values of the same below respectively for each of the parameters. The axial force is the same in value as the reaction horizontal force to maintain static equilibrium, and the combined effect is to compress the part. Hence, we associate the axial force at this section with a value of minus 3 kilonewtons as per our sign convention adopted. We again note that the sign convention is just a matter of convenience, but interpretation is more important. Somebody else may treat the axial force obtained as positive, but it is important to interpret it as compression and not tension. For the shear force, the value is the same as the reaction force at A for equilibrium. We see that the combined effect of the shear force and the reaction force is to create a clockwise couple. Hence, we consider it as positive in sign. Lastly, the reaction force at A creates a sagging effect of bending about the section, and hence we consider the resistive bending moment as positive with the value 2 kN times the distance x. Let's say the distance is 10 centimeters or 0.1 meter. So we have the bending moment as plus 2 kN times 0.1 meter, and that's equal to plus 0.2 kN meter. Likewise, the part created by the second section is also shown to be in equilibrium by the same set of values as in the last case, since there are no intermediate loads acting between points A and C. The values will also be uniform throughout till we proceed to the section just to the left of C for both the axial force and the shear force. Let's say the section is at a distance of 0.5 meters from the reference. So, the resistive bending moment is 2 kN times 0.5 meters, and that's equal to 1 kN meter. We see that the bending moment is a linear function of the distance of the section from the reference. Hence, we get a linear plot. Now, when we cross point C and cut the beam at the location just to the right of C, we are now including the downward vertical load of 4 kilonewtons and the leftward horizontal load of 3 kilonewtons. These values shall add up to the reaction forces, and now we assume the system to behave linearly and add the effect of each, that is the reaction force and the load at C, to sum up the effect at the cross section as per the principle of superposition or superposition that we have learnt in the last lecture. The new value of axial force will be minus 3 due to the horizontal reaction force at A and plus 3 due to the horizontal load at C that creates tension in the part between point C and the section. The resultant shear force value at the section just to the right of point C will be plus 2 kN minus 4 kN at C, and that equals minus 2 kilonewtons at the section. These axial force and shear force values shall now continue to remain uniform till we encounter the end of the beam, that is point B, where the reaction force acts. This reaction force sums up the axial force shear force values to 0 at the support. Let's say the distance of the section just to the right of C is 1.1 meter from the reference end A. The resultant resistive bending moment at the section is plus 2 kN times 1.1 meter minus 4 kN times 0.1 meter, and that's equal to 1.8 kN meter. If the section is very close to the point C or exactly at C, the resistive bending moment is maximum with the value plus 2 kN times 1 meter, that is plus 2 kN meter, indicative of sagging effect as per our sign convention adopted. For the section very close to the point B, let's say with x is equal to 1.9 meters, the resistive bending moment equals plus 2 kN times 1.9 meters minus 4 kN times 0.9 meter, and that's equal to plus 0.2 kN meter. We again see that this resistive bending moment is a linear function of the distance x of the section from the reference end A. Hence, the plot for the variation of bending moment shall also be a straight line for the span CB. The bending moment is exactly 0 for both the ends, also indicating that the simple supports do not offer any reactive moment to the external loads or applied moments, if any. Hence, by using the method of sections and the principle of superposition and considering the part in static equilibrium, we are able to find the resistive axial forces, shear forces, and bending moments at various imaginary sections of the beam. Henceforth, we shall write equations for the unknown axial forces, shear forces, and bending moments as a function of the distance x of the part under consideration from the reference end. This shall enable us to draw the locus course for the variation of these values along the length of the beam and for mathematical interpretations. In the next lecture, we shall take cue from this example and understand the relation between the rate of loading, the shear force, and the bending moment at any section along the beam's length.